Okay, Shabab. We would like to continue with the second order system, which we have started last time, okay, where we said we would like to do the time domain, okay, analysis and design as well. Okay, we will do the design for the second order system, because the second order system, this is the typical, okay, second order system. Okay, it's characterized by two parameters, zeta and omega n. Okay, so depending on the value of zeta and omega n, the system will behave in a certain way. And sometimes we would like to do a design in the time domain by specifying, by relating zeta and omega n to certain quantities, which we will be mentioning, a little bit later. That's basically the overshoot, the settling time, and the time rise. So in this lecture, we will be focusing on, the characterization of second order system by zeta and omega n. So if this is, if this is the second order system, what will be y of s in terms of r of s? How do I find y of s in terms of r of s?
The negative feedback, you can reduce it.
Okay, so basically, this is what we are going to have. I'm relating y to r. And let me study, I'm taking r to be 1 over s. Let me study, let me look into the response when r is a step function. Okay. How does the various value of zeta and omega n will affect the shape of my response for the step input, let's say. Okay. If I have step input, if r is equal to s, so I'm going to have omega n over s squared plus 2 zeta omega n s plus omega n squared, or I'm factorizing the poles of the system. Okay. Now,
just a minute, Doctor. How you factorize it?
How do I put what?
How you factorize it, and where is the other s now? It's third order becomes second order.
No, this is a third order. I'm just factorizing this portion, this complex number. This is sorry, this pole. Use the quadratic formula. So the roots, let's say S1 and S2, equal to minus 2 zeta omega n plus or minus roots of what? 4 zeta square omega n square minus 4 AC, A equal to 1 and C omega n square, so 4 omega n square over 2. So that will give you what? Minus zeta omega n plus or minus, take the 4 out and omega n out as well. Okay, if you take it out under the square root, so it's going to be omega n root of, okay, zeta square minus 1. And that's basically what we have.
But we didn't multiply the two solutions. You just put them at the right.
No, we just, okay. Look, what I'm saying, those are the poles of my system. And now because I want to discuss the location of those poles. So those are the poles. All what I'm saying, I have second order system. The second order system will have 2 poles.
So the second S here in the denominator should have a subscript, which is 1, 2. Well, because
look, Abdurrahman,
to factorize this, we have to multiply by 2.
Abdurrahman, those are two, you multiply them. Yani basically the concept is that we will have two poles, okay? One is positive, one is negative, and those are your poles. So yes, technically speaking, yes, but what I meant, it is, you know, rather than put it in here, inshallah, okay, next time you want me to put another one, you put one, the plus, and then here the minus. That's what you are saying?
Yeah, just yeah, need to
Okay. It's
understand.
not notation, okay.
Yeah.
So basically, I will have, okay, and here we said, okay, omega n, we call the natural frequency, and zeta is damping ratio. What is a damping? What's a damping ratio? In a system, what's the damping ratio? Usually, if you have oscillation, the damping factor is how fast that factor will diminish the responses, the oscillation, and, you know, make them, let's say, the response will go to zero. So the damping is, you know, how much I can damp my oscillation and bring it to certain steady state value. And omega n is the an oscillation. Think about, okay, think about you have a mass connected, you are suspending a mass in a spring, and it's at equilibrium point. Okay, pull the mass and leave it. There is certain, so you are disturbing your system. When you disturb your system, because of the spring, it will oscillate, isn't it? And ultimately, because the disturbance has gone away, it will settle again to its equilibrium point, isn't it? Are you imagining what I'm saying? Maybe there is a video. If you go to Wikipedia, they have very nice piece of video describing the, you know, damping. Okay. Now, the second order system, as I said, will be characterized by the parameter zeta and omega n. And what we want to do now, I would like to look into the performance of the second order system. This is the system. And we said it has two poles. One at minus zeta omega n plus omega n root of zeta squared minus 1 and minus 1. So I have two roots. I would like to see what will be the effect of zeta by varying zeta on the location of the poles on the j omega axis, on the S plane. Look, suppose zeta equal to 0. What do we have?
You only have complex numbers.
You will have pure complex number. If zeta between 0 and 1, what do I have?
Underdamped?
Which is basically the roots are
Complex?
complex conjugate. If zeta is greater than 1,
Damped.
okay, the roots will be
Distinct.
real. So basically, I would like, okay, while if you change omega n, look, omega n, it doesn't vary, it doesn't make the poles complex or real. It will, all what it will do, it will scale whatever you have. So we are going to take 4 cases, okay, for the various value of zeta. Let me start by zeta equal to 0. Okay, if zeta equal to 0, so where are the pole will be? This will be 0. This will be 0.
Complex.
So minus, plus or minus j omega n.
Yeah, basically if zeta is less than 1.
Okay. Or if you want to put their location, okay, The location they are going to be on the j omega axis. Now, I need the step response. This is y of s equal omega n s over s squared plus this one here. What is y of t will be? What's y of t will be? What do you think?
Is it e to the power minus omega nt cosine with the sine?
No, there is no, because look, the exponent depends on this term, and I don't have this term. So basically, this is the response, pure oscillation. That's why it said n damped. N damped, it means, if you think about it, the response will look like, if this is the one, this is the step, I will oscillate around the one. And damped, it means that the oscillation is not going away. They will stay with me. So it's called n-damped case. When zeta equal to 0, it's n-damped. The roots are on the j omega axis. Just, take it from the Laplace transform table. Okay? Any question here? Now, let me go to zeta between 0 and 1. Those are my roots, and zeta between 0 and 1. We call the case underdamped, and we are going to have, where are the roots will be in this case? Zeta between 0 and 1.
Is in the left.
Okay. In the left, yes. But where?
Complex.
They are going to be complex conjugates. Okay.
Torr of zeta is less than 0, it will be unstable, right?
If 0 is what?
If zeta is less than 0, it will be unstable, right?
Yes. If zeta is negative, it will be unstable. The oscillation will expand. They will not decay. They will propagate more.
Mm-hmm.
Okay. So now, those are my complex. Those are my poles. So one is located here and the other in here. And this is the real axis is equal minus zeta omega n. And this is the...
So we'll have kind of overshoot, and then it will...
That's correct. But let me, before we go in there, what is the magnitude of this quantity? What is the magnitude of this quantity? From 0 to the magnitude, okay?
You take the a square plus b square.
Which is going to be?
Omega n square.
Zeta square, omega n square. Plus omega
square multiplied by
1 minus zeta square. Okay.
Take omega n out.
This will go with the negative, and it's going to be omega n. So this portion is going to be omega n. How about the angle theta? Let me call this a theta, because I'm going to use them a little bit later. So cosine theta equal to what?
Equal to minus zeta.
It's not the minus. I'll take just,
zeta, it's a reference angle. Zeta.
It's going to be zeta omega n over omega n, which is equal to zeta.
Zeta.
Okay. Now, as you said, use the table and get y of t. So this is y of t. And in this case, the response look like, if this is the one, this is one, I will overshoot. Okay, so this is what we call underdamped response, where I will overshoot, okay, my response, and then I will oscillate. Because look, as time goes to infinity, the exponent will go to 0. And this term will go to 0. I will have only one.
So,
Yes.
can you just repeat how you found the angle, theta?
How do I find the angle?
Yeah.
Okay, suppose this is theta. Okay. What I'm saying, what's cosine theta? Cosine theta is the adjacent over the hypotenuse المجاور على الوتر.
And the magnitudes or
The
everything?
magnitude, yeah, I'm taking magnitude.
So what happened to the square root of 1 minus zeta squared?
Okay, what happened? Because look, we said this is omega n. This is what we have. This is zeta omega n over omega n. We already, this is equal, this, okay, from, we already find that omega n, I mean, the hypotenuse equal to omega n.
Oh, yeah, I see.
Okay.
Yes.
So this
That's
is
clear, thank you.
basically what we have. Any other question?
No, clear, thank you.
Okay. Now, let's go and take one more thing. If zeta equal to 1. If zeta equal to 1, what will happen? Just one second, شباب.
دكتور هي نفسها طبعا لو اخذت التان انفيرس صح؟ تان انفيرس اوف
دقيقة يا عبد الرحمن. العيسى علي العيسى.
Yes.
If zeta equal to 1, what will be the roots?
It 2 minus 2 omega n and 0.
It will be minus, no, this one, look, this will be, if this is 1,
0
this will go. So I will have basically two
minus omega.
identical poles. Okay. I will have two identical poles located in the same place. Do you agree? Zeta equal to 1. So this will go, this portion, and I will have minus zeta omega n equal to 1. Sorry, zeta equal to 1, so it's going to be minus omega n. Okay? Since, you know, it is second order, it means that I have two poles located in the same place. A repeated pole, repeated roots. This is basically what I'm saying. Abdurrahman, do you have a question or comment?
بس كان دكتور في الزاوية الثيتا you take the cosine inverse of zeta, which is the same as tan inverse of 1 minus zeta square under the square root.
Exactly. You can, okay, whatever. Yeah.
تمام.
Okay, now the response, again, if you basically, okay, what's the response of the system? I have two people.
Can you damped.
Okay, so basically, the response will look like y of t equal 1 minus e to the power minus omega n t, 1 plus omega n t times t. This is because of the repeated pole. And the response will look like, if this is the one, it will be, this is the case. We call it critically damped response. Obviously now, we would like to see the last case, which is
Overdamped.
basically zeta greater than 1. If zeta greater than 1, okay, what do we have? If zeta greater than 1, where will be the location of the poles of the system?
the right.
Jason,
Yes.
what will happen if I have zeta greater than 1? What will happen to the pole of the system?
The balls would be in the right.
No, no, it is in the left, because as Abdurrahman mentioned, if zeta is negative, the system, now the pole will be real. Basically, this is going to be positive quantity, okay? And it's always, you can prove that this is greater, because look, zeta omega n, and here I have zeta squared, I'm subtracting 1 from it. So definitely it's going to be, this term is going to be less than this one. So it's always, we are in the left half plane, but they are real. They are not complex. This is basically what I'm trying to say. What you will have two poles, S1 and S2. They are always real, and they are in the left half plane. They will be in the right half plane if zeta is negative. Okay. So if this is the situation, what will be the response of the system? You can decompose this one into two poles, and then the response will look like, or y of t, sorry. Okay. Where is y of t? Well, y of t is going to be, I mean, somehow
disappeared.
you know, well, if you look into the, okay, so it's going to be basically y of t equal to 1.
Maybe because it's easy, Doctor.
E to power minus S1t, okay, plus b, let's say whatever those values, a and b, minus S2t. And the response, if you want to plot it, is going to be, again, similar. It will be very similar to the critically damped case.
It'll take more time.
It will take more time.
Yes, because the previous response, we have omega n as a coefficient, so this will make the or we have a t even also. We have t in the coefficient, so it will make the response
Basically,
faster.
but however, in general, it look like the same. But you know, usually, you know, many applications, we would like to, you know, use the critically damped case. Certain application, we need the overshoot, but you know, for example, if you have a DC motor and the output of your DC motor is a position. So which of the, you know, oscillation or which type of response you would like to use?
The position.
Yes, you want to control a position.
So it shouldn't take more time. It should be critically damped.
Why not overdamped? The overdamped is faster.
Overdamped is faster.
Yes. Sorry, underdamped.
No, underdamped we will have a problem actually.
Why?
Because of the overshoot and the oscillation.
Exactly.
So we will have a problem.
If you have a motor and you want to control, you know, your output is a position, you would like to go to a certain position. Okay. So in the underdamped, there will be overshoot and then oscillation, and you reach. While the, you know, overdamped, it will reach, but it will take more time. As a compromise between the two, you will use the critically damped case, where it's a little bit faster, but there is no overshoot. Okay.
Question.
Yes.
بالنسبة يعني for just to have the full picture يعني. I don't know whether we will be covering this in the coming slides. For higher order system, this is for the second order. You know, most of our systems are higher order than second order. Second order is just for a couple of systems. For higher order systems, do we have the same critically damped, overdamped, and underdamped responses, or we'll have totally different thing?
If you remember in the last lecture, at the beginning of the lecture, I said we will be covering the idea of, dominant poles. What we are going to study in this course, we will be studying higher order systems. However, the dominant poles are of the second order. So we ignore those and we will be, we approximate those higher order systems by the effect of the dominant poles by, okay. So as you said, zeta, the overshoot, the underdown, the settling time, the overshoot, this is in terms of the parameter of second order system. For higher order, no, we will approximate them if, if the roots are far away from those dominants. If not, it will be, yes, I agree with you, it will be difficult. You will, okay. You could, Abdurrahman, you could do, okay, for example, the overshoots. Suppose you have 10th order system. Use MATLAB, okay, and from the graph, you can determine, okay, from the graph, because this is, the MATLAB will numerically will solve it for you and plot the response. So look into, if the response do like this, for the 10th order, you can calculate from the graph, but not mathematically. There is no simple formula. If you are talking about simple formula, no,
I see now.
simple formula.
So it will be numerical way of.
It will be numerical, yes. And from the concept of overshoot, what's overshoot? Overshoot, you are going beyond. Okay, you have a step over the step, so you can graphically you can find it. But if you are talking about formula, numerical if formula you want, closed form solution, I don't think it's available. Either you approximate or you will do it numerically. Okay, but we'll be talking about the case where we have the dominant poles. Now look in here.
Doctor,
Yes.
the critically damped response is slower than the underdamped, right?
Yes.
But doesn't have overshoot.
But it doesn't have overshoot. This is basically, look, this is the 4 cases. This is the response for step for the 4 cases. This is zeta equal to 0. This is undamped. Okay, this one, zeta less than 1, greater than 0. This is zeta equal to 1, and the last one, zeta greater than 1. So this is a summary of the response for the 4 cases.
So undamped is inconceivable, right?
What do you mean?
What I mean is that because if it will sustain doing oscillations, it means energy is infinity.
Well, theoretically speaking, yes, you are. This is basically, think about a system with a pure capacitor and inductor only. Okay, so the energy will what? Will oscillate between the two. Isn't
Yeah,
it?
but of course it will be with some time. It will be
No, yes, you are right. What I'm saying, ideally, yes, this will stay forever. But we know from life that, there is certain,
thermodynamics.
dissipation in the energy, and that's not the case. Okay, so look, this is another, graph where we, zoom on zeta more. This is 0.1, 0.2, 0.4, 0.7. As zeta increase, the overshoot will decrease until it will disappear in the critically damped case. Okay? This is another shot at it. Now we come in here. We would like to relate, or we would like to sometimes do design. You are given certain system, second order. We are going to focus, let's say, the case of the, underdamped case. Let's focus on the underdamped case. And suppose you would like to, specify the percentage overshoot you would like to have in your system, and how fast is your system, how fast you reach to the steady state, or what is the time you need at the beginning of the response to go to 90% of the your response, your final value. Those are quantities of importance, and we would like to relate them to zeta and omega n. So we are going to relate the maximum value of the response due a step, and when that will happen. We will look into also the settling time, how fast the response will go. We also, as a measure of the speed of the response, we will take the time rise, which is basically if you go between 0.1 and 0.9. This is, the way it will be used, even though, I mean, technically speaking, it should go between 0 and 1. But usually, we will use the time rise as the time needed to go with the response from 0.1 to 0.8. In here, all of those quantities which I mentioned, they are related to the transient. Okay. For the steady state, we will come a little bit later. The error, we will come later and talk about how do I eliminate the error if there will be an error in the system. But for the time being, let me relate the maximum value. When that maximum value will happen, the settling time and the time rise. So the settling time is defined as the time needed for the response to go within, let's say, certain percentage of the final value. Ideally, you would like to go to 1, but that might take long time. So you have to be practical. Okay? So you take certain range, which is, let's say I will tolerating my response to be, if I reach, let's say, within 2% of the final value, that will be fine with me. In certain application, maybe within 5% of my final value. Okay? Any question here? So let me come again to the second order system. As I said, I would like to find TP, percentage overshoot, TR, and TS, and I relate them in terms of zeta and omega n, because zeta and omega n, they characterize the second order system. So suppose I have, this is my system, and I have step response. If you remember, we have shown that the response, if the system is underdamped, this is the response. Okay? Now, first of all, let me start by finding the maximum overshoot or the peak time. How do I find the maximum overshoot? What do I do? How do I find the maximum overshoot?
Differentiate the function.
Exactly. Differentiate it and set it to 0 to find the maximum value, isn't it? So you take the derivative of y, okay, whatever that will be, set it to 0. That will give you the time, TP. Take TP and substitute in y. That will give you the maximum value. So let's do it a little bit differently. The concept is basically you differentiate this one. But look, this is a little bit complex. Very complicated, isn't it? This is complicated. How about if, let me take Laplace transform of, okay, y dot. Because ultimately that's what I want. I want y dot. What's Laplace transform of y dot?
sy minus y
S times y of s.
minus the initial condition.
Minus what?
Minus y at 0.
Okay. Take y0 to be 0. So this is basically what we'll have. This, look, just this is, we are getting it from the transfer function anyway. Assume the initial condition to be 0. So if this is the case, so this is equal to what? If you multiply this one by s, so what do I get? I will get omega n square over s square plus 2 zeta omega n s plus omega n square, isn't it? So what is it in the time domain? What is y dot of t equal to? What do we do?
Fraction.
Well, or look at the Laplace transform table.
برضو Laplace transform can do the job.
Laplace transform table will give you, okay, this is from the table. So basically,
Good.
y dot equal to this quantity.
Now sine cannot, we have to equate this to 0, right?
Give me, okay. Hadi.
Yes, doctor. Yes.
Okay. How do I, when y dot will be 0? Because with maximum value, when y dot will be 0?
When sine equal to 0?
If the sine equal to 0, you're absolutely right, because this cannot be. So the sine equal to 0, when the sine will be 0. So that will be if I have omega n, okay, root of 1 minus zeta square t equal to n pi. Isn't it? The whole thing, this is equal to n pi. If n, where n equal to 0, 1, 2, and so on.
Well, 0 we cannot.
Why not, Abdurrahman? You are absolutely right.
لأنه يصير عندنا زيتا 1 ويصير عندنا 0 في المقام فمشكلة.
Will 0 will be, look. Okay. With 0, basically, look, this is the response look like. If n equal to 0, we are at this point. Okay, because t equal to 0, basically what we are saying, t equal to 0. If n equal to 0, t equal to 0. So we ignore it. We go to the n equal to 1. Because it is the global maximum. So if n equal to 1, what do I have? So if n equal to 1, okay, if you let n equal to 1, so Tp will be pi over omega n root of 1 minus zeta square. And this is the first parameter. We are evaluating, okay, again, let's go back to what this, okay, so basically we find this one. And it's function of zeta only. Okay, now if I want to find the overshoots, how do I find the overshoots? So I substitute TP at Y. So this is basically, if you remember, this is Y. Now substitute TP equal to this quantity. What will happen to this one? If you substitute 4T in here, okay, substitute 4T by this quantity, what do we get?
Pi plus theta.
Pi, so it's going to be 1 minus 1 over root of 1 minus zeta square, e to power minus pi, exponent to minus pi, zeta pi over the 1 minus zeta square times sine pi plus theta. But what's sine pi plus theta? Sine pi plus theta. What does this equal to? Anybody, Shabab, from
Sine theta the same.
minus sine theta.
اي صح تمام.
Okay, so I will have, okay, so this is going to be, okay, I will have a minus sine theta, or this is going to be 1 minus, plus 1 over root of 1 minus zeta square, e to power minus zeta pi over root of 1 minus zeta square, okay? But let's go back. Remember theta, what I told you we needed? This is my pole, which is in here I have j omega n root of 1 minus zeta square, and this is minus zeta omega n. And we said this is theta. So what's the sine theta? Equal to what?
It will equal to
1 minus zeta.
Omega n.
1
Yeah.
minus zeta square over
It's going to be
under the square root.
1 minus zeta square.
that's it, yes.
Substitute in here, you will
Cancel with
1, you get this formula. Okay?
this is the value of the function at the peak time. هذا هو الاوفرشوت.
لا هذا البيك. This is not the overshoot.
هذا البيك طبعا تطرحه من الستيدي ستيت يعطيك الاوفرشوت.
Exactly. The overshoot, you subtract the peak minus my step size. The step size is equal to 1. So the overshoot, this is the overshoot. And we put it in percentage because it's fraction.
معلش يا دكتور كيف جبت انه الستيبز 1 حسبت
كيف ايش؟
اي بحكم انه ستيب ريسبونس يعني فاخذت الانفينيتي المفترض يكون 1 مظبوط. نعم مظبوط.
Okay. No, yeah, because look, again, if you go back to the definition, this is the way we define it. Okay, in here, look, this is the maximum value, and this is the step. In the overshoot between the step and the maximum value. If my step is 2, let's say, my MP is going to be definitely more than 2, and so on.
I would increase by the same, Doctor, right? To increase by the same amount.
Not necessarily. It depends on the system, of course. But what I'm saying, it is the peak. The overshoot will be the peak value minus the step size. In this case, the step size we are saying 1. So I'm subtracting from 1. Okay. So this is basically, if you want, okay, if you want to design a system, I'm relating in here zeta into the percentage overshoot. So the percentage overshoot is function of zeta only. Okay. Now, if I would like to find zeta, you solve this equation by taking the inverse or by taking the ln of both sides and solve. In the exams, you don't have to worry about memorizing those. Either we'll let you to bring a formula sheet or we'll provide. So basically, what we are saying in here, the overshoot is function of zeta only. Now, if I need, certain overshoot from my system, so I will set zeta to get certain overshoot. I can, from the overshoot, I can determine what's my zeta. Or if I want certain overshoot, so I select certain zeta to give me that overshoot. Now let me go, because this is, I need something related to omega n. So let's talk about the, settling time. Okay, the settling time, if you remember, okay, this is the one, let's say. The settling time, I define it. It is how much, if I will allow my system to be within certain, range. Okay. So the settling time, in order to solve the settling time, let's say, assume I want to be within the 2%. So if this is 1, so either I would be at 1.02 or at 0.98. Within this range, I will be. If I want to take the upper one, so let me take the equation of the envelope. Okay, this is basically the equation of the envelope. Okay, so from this equation, we will be solving TS, and TS is going to be, we approximate it to be TS equal 4 over zeta omega n. So look, this formula is valid if I'm taking the, my accuracy is within 2%. If I change this one, let's say I'll take within 4% or 5%, definitely the formula will be changing. It depends on. So now look, the settling time will be depending on zeta and omega n as well. We will have also, we could relate the time rise, okay, to the omega n and zeta. The time rise, basically, you look into the response, it is not easy to solve. They will do approximation to go between 0.1 and let's say 0.9, okay, and 0.9. You do certain linear approximation. The approximation is being done. This is the approximation. And this is valid for zeta between 0.3 and 0.8. If you want to go outside this range, you might get a little bit of error. So look, if you want to do a design, if you want to design a system, you have to specify two quantities: overshoot and settling time, or overshoot and time rise, or time rise and settling time, because you need zeta and you need omega n. So you need two parameters, okay? But we cannot use, overshoot, time rise, and settling time together to get zeta and omega n. That might conflict. Okay? Any question here?
And we use two, Doctor, to get zeta and omega n. Either
Yes.
time rise with settling time or settling time with...
Yes. Hopefully that will, give you the third parameter depending on your calculation.
So now, Doctor, it is 4 parameters or 3?
They are 4 parameters. No, okay. What you would like to have 4 parameters, but what I'm saying, you characterize the second order system by zeta and omega n. Okay. So you solve as if you have an equation. Let's say I have a1 x1 plus a2 x2 equal to 1, let's say, and I have 2a1 x1 plus 3a2 x2 equal to 3, let's say. I solve those. if I have a third equation, what will happen?
It will be dependent.
Exactly. That's what I'm saying. Otherwise, there is no solution. Okay, so I will use two of, usually they will give you two. Usually they will give you two. The third is going to be dependent, as you said. Because otherwise, there is no solution.
Okay, it's clear.
Okay? Okay, so we'll stop in here. Any question before we stop? Have a nice weekend.
يعطيك العافية دكتور.
الله يعافيك. بس دقيقة. Let me stop the recording.